Hi, folks. Today's topic, finding zeros algebraically. So we're going to get into this more tomorrow, or next time, I should say, when we do finding zeros graphically, but I can give you a quick rundown here. Zeros are where the graph hits the x-axis. Zeros are the numbers that when you plug into the function, give you an answer of zero. We have another name for these. You might see the phrase roots or solutions or x-intercepts. All those and zeros, all those phrases mean the same thing. It's these values. They're the x values for which the graph has a height of 0, and we're going to try to figure out where those values are. So there's a lot of different, as you can tell by all the different boxes. There's lots of different styles. I'm only going to do one example of each style. You're going to have to dig into it with the homework, and then you're going to have to memorize what style it is. So in other words, not memorize it necessarily, but be able to recognize the style and then how to algebraically manipulate that style to find out the zeros. Well, let's get into it. So my first style is when everything is already factored. This is called already factored. Right? Everything is already connected by multiplies. They're in their own groups. If I want to figure out where this thing equals 0, where this function equals 0, we do this move called ZPP, the zero product property. So the zero product property says if you have some things multiplied together that equal 0, at least one of those things has to be 0. Now, they all could be worth 0, or only one of them could be worth 0. That's why at the end we're going to write down all the possible numbers that you could just tell, like right off the top. You could say that, what if this was 0? If you put 0 in here, this won't be 0, this won't be 0, but when you multiply them, they'll all equal 0. That's the basis of the zero product property. So once you've got everything factored, you can set each term equal to 0. That's the ZPP. So I set each piece equal to 0. Now I go from an equation that's fairly complicated to 3 equations, but each one of those 3 equations are really easy to solve. So I would square root both sides to kill off the squared. Now normally you'd have to do plus or minus, but there's no such thing as positive or negative 0. I bump over the 2, I get x equals 2. Now this one's a little sneaky. Who's farthest away from x on the same side? Cubed. But what kills cubed is cube root, and the cube root of 0 is still 0. Then I would bump over the 1 and make it negative, and I'd divide by the 3. So I would get x equals negative 1/3. Now notice I haven't boxed anything in yet because of this thing called the fundamental theorem of algebra. The fundamental theorem of algebra, which is going to be, I think, 2.5. We're going to get into it, but all we need to know right now is that the number of zeros has to be the same as the number of x's in the original equation. And what I mean by number of x's is not 1, 2, 3. It's 1, 2, 3, 4, 5, 6. Now, why did I count 2 of them here? Because what's x squared? X times x. There's really 2 x's here. Why did I count 3 of them here? Because this is really 3x plus 1, 3x plus 1, 3x plus 1. Now, I don't want to have to write that all these different times. So the phrase that we use is multiplicity. This 0 is going to occur twice because that x equals 0 will happen 2 different times, one for the first x and one for the second x. So underneath this, instead of writing x equals 0 twice, we write mult 2. Now this mult stands for multiplicity. It's how many times that 0 occurs. Now, how many x's were here? Only 1. How many answers did we get? Only 1. Now, when it's mult 1, you don't have to write the mult 1. Think about all the times we've solved equations from algebra 1 until now, and we never had to write this mult stuff before. So we still don't have to do it when we're talking about mult 1s. This 0 occurred 3 times, so underneath here, I'm going to write a mult 3. Box it in. put it up on my fridge. So a quick little check. There are 1, 2, 3, 4, 5, 6 answers. There are 1, 2, 3, 4, 5, 6 answers. Worked out. Okay, so that's when everything is already factored. Boom, everything's factored. You're good to go. What happens when everything isn't already factored? Well, what do you think? You factor. So this is our old factoring method. This is an X factoring. If you don't remember how to do this, go back and look in Unit 0 of our Google Classroom. You can see there's an example or a video on factoring. Okay, so I got to find two numbers that add to make 5 and multiply to make 6. Well, 2 and 3 or 2 or 3 or 6 and 1. But 6 and 1 of them would need to be a negative, so it's got to be 2 and 3. So now I can factor this. So that's got to be a 3. It's got to be an X. It's going to make the 3. It's going to make the 2. And I want to add them both together. If you can't do what we just did, you need to go back and look at our notes in section 0, 0.2, I think, maybe 0.3, I can't remember. Or stop in after school and we can work on it together. But you must know how to factor. It's so basic. It's such a basic skill in this class that you have to be able to do it fairly quickly to be successful. Now, we're trying to find the zeros, which means I want to figure out when this equation equals 0. As it is, this equation is fairly complicated because we've got two things multiplied together to equal 0. What we can do is the ZPP. The bad part is that we now have two equations where before we had only one equation. But the good news is these equations are really easy to solve. Bump over the 2, divide by 3, that's negative 2/3. Bump over the 1, that's negative 1. How many solutions? 2. How many x's? Now, when I say how many x's, I mean how many total x's, the highest exponent of x's. Like over here, it kind of feels like there was a lot more x's than there. Shouldn't we count this one as well? No. It's called the degree. If you distributed this, the leading coefficient would have a power of 6. So when we're talking about the fundamental theorem of algebra, I'm talking about the degree, not total number of x's. It's what you would get after you distribute it. All right, looking at the next one. All right, I try to x factor this. So I take the first thing times the last thing, that's negative 24. Thing in the middle is negative 4. 1 and 24, 2 and 12, no. 3 and 8, no. 4 and 6, no. Nothing works. Nothing works. When nothing works, what happens? When factoring fails us, we go to our good friend called the quadratic formula. You remember the song? Do you remember the quadratic formula first, I guess? X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. I'm sure if you remember the song. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a, rah, rah, rah. So, if we're going to do the quadratic formula, we first have to identify who is a, who is b, who is c. So, a is always the term in the coefficient of the x squared term, so that's negative 1. B is always the coefficient of the x term, so for us that's negative 4. And c is always the constant. The constant in this case is the 24. Now we can start plugging in a chugging. X equals negative b. Well, look, our b value is already negative 4, so negative b would actually be positive 4. Plus or minus, and I always put the root in after I do the next part. B squared, so that's negative 4 squared. My advice, put that in parentheses. You don't want to mess up and accidentally square without the parentheses. That's that stuff we did also in Unit 0, where you don't want to make that calculator mistake. times minus negative 4 times A times C. All over 2 times A. All right, when you clean this up, back in the day, you used to be able to type almost all this in your calculator. You get some messy decimal. Now we're in pre-calc. We want to get nice exact solutions, nice simplified exact solutions, which means we need to clean up a little bit at a time. Start off with cleaning up what's under the root. So I'm going to do not the root, notice. I didn't say do the root, do what's under the root. So that's the negative 4 squared. Subtract 4 times negative 1 times 24. You should get 112. So now I'm doing 4 plus or minus the square root of 112 over 2 times negative 1 is negative 2. There are two things that I need to fix here. The first thing I need to fix is this negative on the bottom, so I'm going to bump that negative up in the next level. The other thing I want to see is if there's any perfect squares that go into 112. So over here in the corner, 112, and I'm going to start dividing it by the perfect squares. Is 112 divisible by 4? Yes, 4 and 28. Now remember, one of the checks that you can go through is if another perfect square goes into this, you should keep looking. And a 4 goes into there, so I know I'm going to keep looking. So 112 divided by 9, no good. 112 divided by 16. And remember this trick, if you get a perfect square and the result is prime, you can't go any further. So 16 and 7 are my better choice. So now I can break this up into 4 plus or minus. I forgot. I'm going to bump this negative up here. So that's going to become negative 4. What's a plus or minus? If I switch the signs of plus or minus, it's still going to be plus or minus. It's going to be minus plus. Same thing. So I'm not going to mess with that. But I am going to rewrite this. So I want to do the square root of 16 times 7. So that's 4 escapes. 7 stays in. All divisible by a positive 2. Now, I still wouldn't give full credit at this spot because you can clean this up a little bit more. Everything has to be divisible for you to be able to reduce. The 4, and the 2 are all free. We don't have to worry about this because it's connected by mul, so we're still allowed to divide. But these are all, everything that's free is divisible by 2. If this was a 4 and this was a set, I don't want to say 7 because that's a 7. Let's say this is a 4 and this is a 5 and this is a 2. That's it. That's the best we could do. But because these are all divisible by 2, we're going to divide them by 2. So I would get negative 2 plus or minus 2 roots of 7 as my full credit answer. What happened to the denominator? Well, it turned into a 1, and when you have a 1 on the bottom, you don't need to clean that up. All right, so those are our first 3 methods. Already factored, ZPP. Factor, ZPP. Can't factor, isn't already factored, so then I'm stuck with doing the quadratic formula. So you're going to have a progression here. I'll show this again at the end. But you're going to have a progression here where you want to go through and follow a process to see if you can find those zeros. Okay, this next one, there are 2 ways to do this. There are 2 ways. I'm going to show you both ways, and you can choose whichever way you want to do. As I look at this, I notice that there's only one x. Okay, there's only one kind of x. So when I ZPP this, if I take 16x squared minus 9 and I set it equal to 0, I can just solve like I did back in Algebra 1. Who's farthest away from x on the same side? Minus 9. Who's farthest away, the squared or the 16? 16 is connected by mult, so that's weaker. So I would kill that next. And now, who's keeping x from being by himself? Squared. And here's where a little trick that we talked about earlier too. When you square root is on fire. We don't need no water. We just need a plus or minus. So don't forget that you have to have a plus or minus whenever we square root. Okay, so this method, just called solve. Now, why couldn't we just solve these? Well, these x's were all connected by multiply. These x's were never ones that we could ever get x by itself. In this situation, I could get x by itself and go from there. But in this special case, you'll notice that 16 and 9 are special numbers. What do we call those numbers? Call those numbers perfect squares. So you could also solve this using our method called dopes, difference of perfect squares. So when I take my 16, x squared minus 9 equals 0, I can factor that into 4x minus 3 and 4x plus 3. Now I can ZPP this. X equals, bump over the 3, divide by 4, that's 3/4. Bump over the 3, that's negative 3, divide by 4, 3/4. How many solutions are here? 2. How many solutions are here? 2. Let's talk about that up here as well. There's 2 solutions here because this is positive 3/4 or negative 3/4. Remember, this is an x squared, so its degree is 2, so it should have 2 answers. Same thing here. Negative 2 plus 2 root 7 is a number, and then negative 2 subtract 2 root 7 is a different number. So going back to this problem, I don't care which way you do it. You could pick and choose. Let's try to do this one using solve. So as I try to solve this, 16x squared plus 9 equals 0. Bump over the 9, divide by the 16. I would get negative 9/16. Who's keeping x from being by himself? Squared. What kills squared? Square root. Square root. And then we have a problem here. Because what are we trying to square root? And if you go back to our last unit, one of the 2 problems that you have when you're looking for a domain, the big problems in mathematics is we can't divide by 0, nor can we square root a negative. Now that's talking about over the real numbers. So we would say no real zeros. But that's just a temporary situation. We're going to get into those imaginary. I don't know if you remember square rooting negatives in Algebra 2. But you can actually square root a negative. Now don't forget, we square rooted, which means we need a plus or minus. Square root of 9 is 3. Square root of 16 is 4. But because that was negative, we would have an I. But we haven't done those I's. So if you don't remember this part, that's okay. This is coming later. In, I think, section 2.76. I don't remember. And I'll say 2.6. We'll see what happens. See how close I was. So, if it's already factored, ZPP. If it's not factored, factor ZPP. If you can't factor, quadratic formula. Then it's done. Notice it says x equals in the quadratic formula, so your solution is done. Solve. That's when if you only have one kind of x, and you can just move x, get x by itself. Or solve and dopes will look the same a lot of the time. Be careful, this is not dopes, this is soaps. Why is this called soaps? Because this is the sum of perfect squares, not dopes. So there is no way to factor this over the real numbers, but we will get into that later on. All right, and then the last ones, I don't have a great name for these. I just call these the higher exponents. So like this is to the 6th, this is to the 4th. All these other ones are like to the seconds. So what happens when you see a higher exponent? It's going to fall into one of 2 categories. The first category is, as you're looking at this, do you see anything that your math voice is yelling at you? Mine's hollering. Mine's hollering factor out. Because I can see that every one of these is divisible, at least has 4 x's in it. So this move is called factor out, also known as GCF factoring. I usually call it factor out, but I think Wojo calls it GCF. So what I want to do is I want to see, what do these all have in common? They all have at least an x to the 4th. Now sometimes they'll have a coefficient in common as well. So if this was a 2 and this was an 8 and this was a 6, I could factor out that 2. So now we've factored out x to the fourth. What does that leave behind? In other words, what would I have to write here when I distribute to get that back? So I'd need a 2 and I'd need 2 x's. I got 4, I need 5, I need another x. I got 4, I would just need the negative 6. So from here, sometimes this thing is not factorable again, and then we've got to go back to our good friend, the quadratic formula. Luckily, in this case, this is factorable. Let's just do a quick double check here. This factors into, what's that, negative 12 and 1, so that would be 4 and negative 3. Now, this x to the fourth is still out there. We can't get rid of that. So that's x to the fourth times the quantity, so that's got to be a 2 and an x. And I've got to build a 4, so this has got to be a 2, and I've got to build a negative 3, so that's got to be the negative 3. Now look, once we factor this, we're into already factored mode, which means we can just ZPP each term. So x to the fourth equals 0, 2x minus 3 equals 0, and x plus 2 equals 0. Now I can solve this, x equals 0, but be careful. Well, let's just go through, I'll point that out in a second. 3 halves, x equals negative 2. 1, 2, 3. How many zeros do we have? 1, 2, 3. How many are we supposed to have? To the sixth means we're supposed to have 6. So where's 3 of them? Where are the other 3? Right here. This is x to the fourth, which means this term has a multiplicity of 4. And then the last style, I don't have a better name for this. This is the only one this is just weird to me. It's just weird. Now, a dead giveaway for a weird is when you have this situation where this is an x to the 4 and this is an x to the 2. So we're going to factor it just like we factored this, where this is an x to the second and an x to the first. Weird, all the ones we see are going to be 4 and 2, but they could be all sorts of different ones. They could be x to the sixth minus 10x to the third plus 9. That's another weird. X to the eighth minus 10x to the fourth plus 9. That's another style of weird. X to the 12th. Subtract 10x to the sixth plus 9. That's a weird. X squared minus 10x plus 9. Now that's not the weird, but that's how we're going to treat this. This is very easily factorable. X minus 9, x minus 1. So we're going to factor it the exact same way, except we've got to make sure that these, see how this is x times x makes the x squared? We're going to adjust these so that it could make whatever that exponent has to be. So I'm going to factor this just like normal, x minus 9, x minus 1. Then I'm going to go back and say, what would these exponents have to be to create that x to the fourth? I'd have to make them both squares, because x squared times x squared would make x to the fourth. And let's just double check that that actually worked. X squared is minus 1x squared. Negative 9 would be negative 9x squared. So minus 1x squared minus 9x squared would end up being negative 10x squared. And then negative 9 times negative 1 would be positive 9. What is this now? We've got parentheses. What is this now? This is factored. So if this is factored, that means I can ZPP. X squared minus 9 equals 0. X squared minus 1 equals 0. Bump over the 9. X squared equals 9. Bump over the 1. X squared equals 1. Who's keeping x from being by himself? Squared. What kills squared? Square root. Square root. Square root is on fire. We don't need no water. We just need a plus or minus. So x equals plus or minus 3. X equals plus or minus 1. Let's talk multiplicity. This is supposed to have 4 solutions. How many solutions do we have? 1, 2, 3, 4. All right, so like I said, you guys are going to have to memorize all all these steps. Now, it feels like it's overwhelming, but when you break it down and you start to go through the list, and keep in mind that you're always trying to factor, it's not as overwhelming as it seems.